Welcome to Poultry in Motion from the H&M Enterprise, sponsored by Cooper Farms. Cooper Farms is committed to producing quality turkeys for consumption by the public. This consists of 7 million turkeys raised annually, with 100 million pounds of meat cooked and 15 million turkey eggs hatched. To maintain this standard of excellence, it is essential to closely monitor the living conditions of the turkeys throughout their growth. Optimal barn conditions consist of the following: ammonia levels below 10 parts per million at turkey height, never exceeding 25 parts per million. Carbon dioxide levels less than 3,000 parts per million at turkey height. Temperature ranges of 90 to 95 degrees Fahrenheit for poults and 40 to 85 degrees Fahrenheit for adults, and a relative humidity range of 40 to 60%. Conditions outside these ranges can cause a decrease in poultry production and profitability. In addition to this, turkeys often pile together and neglect eating and drinking. Due to labor shortages, consistent manual monitoring of these conditions is challenging. These conditions aided us in forming the problem statement to drive our project: develop a device to monitor environmental conditions in poultry barns and encourage the dispersion of poultry to aid in their overall health. Our team seeks to develop an autonomously driving robot that will follow a predetermined path while taking measurements of ammonia, CO2, humidity, and temperature throughout the barn. These measurements, along with their location, must then be transmitted back to Cooper Farms to aid in the maintenance of environmental conditions in the barn. Constraints we must keep in mind include battery life, communication range, rough terrain of wood chips, dusty conditions, limited noise and light emission to avoid disrupting turkeys, and the compatibility with turkeys at all stages of life. The mechanical team, composed of team lead Andrea Hoagland, Kelsey Kirkbride, Caitlin McDermott, Trygve Schmid, and Abby Shaler, worked to further develop a physical prototype to better integrate our electrical system. The initial prototype featured a sloped shell to prevent the turkeys from roosting upon the robot. Other features included smooth edges and a low profile to mitigate the chances of turkeys becoming trapped under the robot or injury from the shell perimeter. The current design now consists of a frame to support internal components. Due to further development of electrical components, it was necessary to increase the diameter and height. The edges were altered from the original sloped edges to a cylindrical profile with a sloped top to make manufacturing more simple and cost-effective. The current design includes a protective box with a small slit containing a filter, which aids in protecting sensors while maintaining airflow and allowing for better physical integration. In addition to designing the body of the robot, the mechanical team also conducted extensive analysis to determine the best battery to utilize in the system. Based on load calculations using the supplied sensors, original microcontroller, and supplied VexBot motors, it was determined that a rechargeable Milwaukee battery with the necessary watt hours and voltage would power the robot for most, if not all, of the barn area. Working on the decision of utilizing a Milwaukee 8-volt battery, the team decided to utilize the Saturn planetary gear motors due to their strong reputation within robotic applications and adaptability to different batteries, should the need arise, as they support up to 24 volts DC and a 2-channel speed controller that is able to be coded via Arduino along with the microcontroller. Each speed controller can run 2 motors, which fits the current demands of this project. While these motors may draw more voltage and amperage from the battery, depending on the shaft length, the runtime should be sufficient to move the robot and its components around the barn and back to the docking station. The electrical team, composed of Asia Haley, Andrea Hoagland, Isabella Langmaid, Harlow Plendel, and Jade Swingram, are currently working to integrate and calibrate the environmental sensors for ammonia, CO2, humidity, and temperature, as well as developing the mapping system to accurately correlate sensor data with the robot's location within the barn. Previously, the team planned to utilize an ESP32 microcontroller using Arduino IDE, as Arduino code was available for all 3 sensors. After getting accurate readings from the sensors, the team then pivoted to focus on navigation and mapping methods. Initially, the team intended to utilize RFID tags around the barn that would be scanned via a scanner equipped to the robot to triangulate its location from 3 scanned tags. After consulting with a wireless communication expert within the university, it was determined that due to RFID range and power demand, it would be an improbable solution. Based on the information obtained, the team decided to utilize a LiDAR scanner to create a map of the barn, IMU, and camera to help orient the robot within the map. Due to these revelations, it was determined that it would be nearly impossible to integrate all of these components with the desired autonomy with the ESP32. The team then decided to switch to using a Raspberry Pi to allow for the team to utilize ROS for better integration of the environmental sensors and navigation systems. The current focus of the team is to gather measurements from the sensors via ROS. In addition to this, the team has been working to develop a web page containing the robot's data to allow for off-site monitoring of conditions. The current website design contains sections which will eventually provide users with live data output, the team's design process, working conditions of the sensors, and optimal environmental conditions for turkeys, as well as contact information. In our future time working on this project, we hope to achieve the following: further advancement in the development of our website, including the alteration of information due to security protocols and sponsor expectations for accessibility to information, sensor integration with the new Raspberry Pi ROS system, full assembly for on-site summer testing, and development of a charging station for the robot. We extend our sincere gratitude to Dr. Rao and our sponsor Cooper Farms for their exceptional support. We also respectfully acknowledge all individuals appearing on screen for their meaningful contributions. Thank you for your time.